still studied in signal processing, and there are no angles to carry out this. But unfortunately, in the fractional case, we did not figure out to do efficiently. In the end, so we just use a very simple procedure. So because we know that this function is analytic, so we just apply a simple rational approximation, specifically this triple A algorithm from Chifson. So, and we found that this algorithm is quite accurate. So if we have good data, and that's the fact. And once we have that, then we just do the recovery of the potential using the simple least square as the second step in the case. Let me just skip the detail here. So in practice, one can carry out this efficiently, for example, using some standard conjugate gradient method plus the adjoint technique to evaluate the gradient of this kind of function. And once we have done that, then we can also recover the source. Just go back to the first step. And let me just show you some numerical results to conclude the talk. So here's the solid curve shows the exact data. And the first step is that we try to extend this exact data by rational approximation, which I denote by the dashed curve. And so that's the extension we obtain. And if we look at the pointwise error, so the error we make is actually very small, like 10 to minus 10 at the initial range. And after that, so it's still quite accurate, 10 to minus 6. So this means that rational approximation, indeed, in this case, can give us a very accurate approximation. And actually, the order of this rational approximation is still quite low, like 6 or 7. So this means that we only have like about 10 terms in this approximation, and the algorithm itself is super fast. So the main message here is that we can use this rational approximation to do analytic continuation quite efficiently. But this algorithm surely is not so stable because we are doing extrapolation. So if the data is noisy, so it does not work so well. And we did not manage how to make it work so for noisy data. And so here's about the recovery of potential. So the black one is the exact data, and then so these in color, so the refer to the recovered. And one can observe that the approximation we obtain so for the potential coefficients based on this analytic continuous data. So it's a reasonable conjunction, but definitely it's not perfect. So and one can see that the algorithm works reasonable, but there are some strange behavior. For example, if you look at the convergence curve, so there are some plateaus. So this is actually not so common. So for example, for standard optimization algorithm. So normally, so we do not see this kind of plateaus and then decrease, plateaus and decrease. So this is quite unusual behavior, and we still don't understand so why we observe this kind of behavior. And so similar observation can be made. So if the potential is non-smooth, so we still have similar, very similar behavior. And once we have the potential, then we can recover the initial condition. So here, so we just assume the source is 0. So we can recover this initial, and this recovery initial condition is actually quite good. So we can see that the approximation is excellent. So there's let me now summarize my talk. So through this talk, so I have shown you that actually, so if we assume that we are considering this sub-diffusion or time fractional diffusion type model, then so using just one single flux point data measurements at one single data point, then we can uniquely recover the order. So without knowing anything else, so we can recover the order. So that's one piece of math. Another thing is that if we know a bit more, so like in the one-dimensional cases, then this one-point measurement actually allows us to recover the order, potential, and the source if if our boundary condition satisfies some very mild condition. And surely, so these results, they are still somehow weak in some sense because it just gives us a uniqueness. It does not say anything about, for example, how stable is this procedure. So if I want to recover this, and how stable will this be? And this kind of issues is completely open, and we don't have any ideas how to do this. And the issue is very delicate because as you can see that some of the steps involves analytical continuation. And another thing is that clearly, so even in the second case I considered, so one should consider a multi-dimensional case. And there are some essential obstacles in such extension. For example, in the multi-dimensional case, we do not have any simple results like for the stem-Liouville problem. So this means that we cannot carry out this straightforwardly. And clearly, so there are also a lot of numerical issues involved. I indicate here a few of them. So for example, here, so if we have noisy data, then this interpolation step will be quite challenging. So actually nobody knows how to do it very stably. And also we have very strange observation about this convergence behavior or axiom. It takes hundreds of iterations to get good results. But normally, so if you apply conjugate gradient method to some other nonlinear inverse form or similar type, so usually it takes like 10 or 20 iterations to get a very good recovery. But here, so there's something very strange happened, and we do not understand. And with this, I think I'm ready to finish. So if you are interested in more details, so you can find all the details in these three preprints. So they are archive. And if you are interested in more about the regularity stuff I described, so you refer to this textbook at Spelunker, so which will appear very shortly. And thank you very much for the attention.
Thank you, Professor Jim, for this very interesting talk. Any question or remark here or at home, you can just unmute yourself and contribute. Not need to write them in the chat. Do we have questions from the chat?
No, dice che non me lo dà perché dall'organizzatore, l'hai bloccato tu.
Hi, thank you for the talk.
Thank you for the invitation.
Do you think that the approach you used for the single order fractional time derivative would be employed also if there are more than one order or a variable order?
Yes, valuable order, definitely it's very, very interesting stuff. So as I think there was one talk yesterday, and you can really see from there, so there are many exciting applications, so which probably multiple order or valuable order or more complicated model probably is needed. Unfortunately, if we try to extend this kind of model, for example, if I try to study them in the context I described, I don't see there's any easy way to go. And one of the big issues is that for these more complicated models, we actually do not have very good solution theory yet. For example, even the regularity theory in Sobolev space or in Hurd space, so we don't know anything, I think. At least I don't know anything. So in that sense, I think it will be highly non-trivial to do extension to all the analysis here to these more complex models. It's very interesting, but I have no idea about how to do it.
Okay, thank you very much.
Thank you. Okay, any other questions or remarks? If not, let's thank the speaker and both speakers of this session.
Thank you very much.
For a coffee, let's meet again at 11:15. Thank you.